Hello everyone, this is Pradyumna here, and in this video I'll be discussing about the DAQ system and its device and softwares. The DAQ stands for Data Acquisition System. Now, you know all about different things which comes under this topic, like microcontrollers. You might know the example of Arduino as a microcontroller, or Raspberry Pi as an Arduino microcontroller. So you can use them to collect data from the sensor which measures the physical quantity. So one part is device and the other part is software. Now here on the left side you can see is the image. This is National Instruments Lab View. This lab view is a GUI based software. So they have designed it in such a way that you can just can directly attach the some functions and your entire program will be created and that will perform the work. You don't need to actually do the programming in the C or Python or any languages. You just directly have to connect some functions points and by using GUI base and you're done and you can go with that. Then this National Instruments also provides some DAQ devices like these. This is a device which is used for the data acquisition system. Now, these devices are really very expensive, and the software is also too expensive. And I recommend to use this software if you're really a professional and belongs to an industry. So that will be very good if you're using this. Yeah. Then there is we have to monitor the data which is being uh, collected. Now here, this is an example which I will show you, an exponentially decaying example. So this is a signal. Now here you can see this it has a quite good SNR ratio. SNR, that is signal to noise ratio. Now signal is about 1000 to 500. Yeah, but there you can see the signal is disturbed by little glitches. So here at the peak point and the below points, you can see there is a lot of glitches. These glitches are also present in on these lines also, these waveforms. If you magnify this, and you can observe that. Yeah. So why these glitches are there? Because this is because any data acquisition system has an electrical noise. Basically, they are built upon the sensors. Sensor, while sensing the physical parameters, they also senses some they also provide some random values. So those random values are also added with the signal and they are disturbed. Or you need to filter out. I'll explain it very soon. So this is what data looks like collected from a sensor and not exact, not that good signal to noise ratio. Actually, this is because it was a cheap sensor. The DAC system was also a cheap at a low price, and as the price reduces, the quality reduces. Next, we have So we will discuss about the devices. First one is the sensor. Sensor is just simple sensing device. Now, if you take example like thermometer, so thermometer is a sensor, but you use it directly by yourself. But when it comes to a computer and computer that physical sensing device should be connected to the computer, then it's basically termed as a sensor. I would say it's a physical sensing quantity, that is, it will convert physical quantity to an electrical voltage, like let's say temperature to an electrical voltage, or acceleration to an electrical voltage, or any value, whatever physical quantity you are trying to measure. Then next part is about signal conditioning. Now you will measure some signal, so there you have to actually what microcontroller does is divides your signal into some parts. Now those are parts into the powers of 2, like 2 square, 2 to the power 8 6, that is like 8 bit 16 bit, in that way. uh, they are actually known as digital levels. So You can like you are splitting the signal into parts. Like if it is about a certain value, and if it is about another certain value, so they will be recorded in that manner, in zeros and one form, and will be stored is the human understandable language in file. Then there is a transfer and receive of the data. So we can transfer the data, we can receive the data by using the micromotor. Now receiving data like is from the sensor, and transferring data to is like any control, like to the control which things, which device which you want to control. I will better explain this in soon. Now about sampling. Now sampling, if you want to search more about the sampling, now first I will mention about Nyquist criteria. You can go to the Wikipedia and search about the Nyquist criteria. So sampling, it will just like, uh, um, it will say it is with the time your device will take what value the sensor has provided, and that value is will be recorded after every intervals of that width. So it is also known as pulse code modulation. After every interval, it will collect those data points. If this interval is very small, then a good quality of signal will be collected. In simple, very simple language, I will say at time one, at and two. So this T2 minus T1, there is a difference. So between this time interval, it takes one sample. So it does this repeatedly, like in a while loop. So in that manner, this sampling occurs and the data is stored. Then serial port. Now, why this serial port is important? Now, let's say you have your laptop and you have connected the data acquisition system to your laptop. So the data will be collected, will be transferred to your laptop to the ROM is through the serial port. The serial for the microcontroller which you're using, it will send the data in the form of packets to the serial port because that's used for accessing. Then there is a software. You can monitor the data through uh, the lifetime by using that software. Also, you can store the data by using various UI commands. Then there is a sensor. There are various examples of the sensor. Like I told you, the temperature sensor. This is the thermostat. Thermostat is temperature sensor. This is the element present here, sensing the temperature, and this is accelerometer. Specific name is given as ADXL345. So then there is now sensors are available in different formats as the manufacturer. It depends on manufacturer what kind of things they add in it. Now, if it is a module or if it is not module, that you should know. If it is not module, then it will be only sensor. So this is an example of thermistor. Here, no module, no such a circuit. This kind of circuit is present. But this is an accelerometer, and it has its own circuit. So what does it do? It has its own analog to digital converter. So it takes the values from the sensor and convert it to perform the signal condition by using the analog to digital converter. Yeah. Then these modules also help to remove the noises like high frequency noises. So they are eliminated. So these kind of functionalities are present in this modules. If it is not a module, then it is only sensor. Then this kind of is that's the NTC20D9. So this thermistor. If there is, you can't see any kind of ADC or whatever circuit is there. Yeah. Also, if it is a module, then there will be also ADCs will be present or not. You should that there's a communication type. It will be present, and also price will be different. Now this is a thermistor and there is no module, so its price is quite low. You can just buy them for 10 to 20 rupees, and this is an ADXL 355. This will be in India will be at least available for at least 400 or 500 rupees. Uh, no, communication type. If it is a module, now then it's communication can be like I2C communication, inter-integrated communication will be used. Then also SPI is also available in this integrated model. Then only sensor, the example is thermostat. Then yeah, when you go for the sensor, like you have to keep in some mind, like why do you need that sensor? Then what are other things which you should know before you buy this sensor? Now, about transfer function. Transfer functions like input to output ratio. Like your input is the physical quantity and the output will be the voltage. What kind of that behavior does it show? Like, is it a linear or a non-linear? You have to look for that. Then, depending on your requirement, you have to know the range. Now, if the range and the threshold noise here you can see. Now, you have a good you have a range like about for an accelerometer, let's say 500 to 1000 and 2000 mm per second square. So this is your working range, and the noise level threshold noise which is present is given by that sensor is about is oscillating between 200 plus minus 200 mm per second square. So it will not be good for you to get to use that sensor because at the low acceleration, the randomly noise will be collected in your data and that will be difficult to analyze. And your signal to noise ratio is in that range and noise is low as compared to what signal you have, then obviously you can go for the cheaper sensors also. So about transfer functions. So let's now look at this graph. So this is voltage and this is input. Input is like any temperature or acceleration, whatever organization. So about temperature. So this, let's say this is the graph for thermocouple or thermistor. I think either of them it is. This is for RTDs. RTD is a linear temperature sensor and it is really good. So the cost is also high. So thermistor is, I guess it is, it should be the one. Here. This should be the thermocouple. So you should look for the transfer function when you look for anything like bias. That's all. Then the qualities matters. So you should go for industry grade sensors. They are actually expensive also, and they why they are called as industry grade because it depends on the quality, the noise, signal to noise ratio they have had. So they are used. Yes, here are some typical examples and pictures I will show which are industry grade. So this is an industry grade accelerometer. Uh, and this is an industry grade RTD that is resistant dependent temperature. That's why it is RTD. So yeah. Actually, this is also accelerometer, but yeah, I haven't used it, so I don't have any idea about this. Then I will demonstrate here about the accelerometer moving with the spring. Now here, this is some kind of weight and this is a plate. This is support for this sensor to be stable in one orientation. And above that there is a spring element, like any helical spring or anything like. So that is present. Now I'll play this video. So as you can see, this is moving. So the waveform which is actually present, so this waveform is generated, the same kind of waveform is generated by using the sensor and is collected with a wire and there is a microcontroller present which is attached to this computer and by using the monitor we are monitoring this data. Now, this sensor ADX35 it has a multi-axis sensor that is XYZ acceleration, XYZ rotation. So all of the data are just shown on the screen. So next is I'll talk about different kind of signals. What kind of signals we get? Now here, this is a signal. Here you can see the acceleration has the value of about 3000. Then it is slightly slowly it is decaying. So it's the same thing, same graph which I showed earlier, but now I have magnified it. We can see how the waveform is distorted, but this this signal is quite good. If you apply some kind of filter, then signal will be quite filtered. But again, now here in this first image, you can see the signal to noise ratio is high, but now here signal is low from 400 to uh, it's 250 or 300. So signal to noise ratio becomes lower, not as high as this, but lower. So, so you can see the signal is becoming more distorted. That is, noise is becoming more. And the original waveform becomes less predominant, and signal becomes more predominant. And here, so this is, I will say, the medium signal to noise ratio. And this, I will say here, this is the last point. This is lower, very low signal to noise ratio. Actually, I already mentioned about the ADLX 345 volt plus minus 200. So in this, the signal is all so noise is more predominant than the original waveform. So you can see it is highly disrupted the original waveform, and in this case, if you're trying to collect the data, then it becomes really difficult to uh, analyze the data further. But even after applying the filters, it becomes really difficult. So I will show you some examples about after applying the filter, what exactly happens now. This domain is taken and filter is being applied about from 400. And we use an algorithm of Savitsky-Goulet with the 31 smoothing points. And and the order is 5. So as the order is increases, your accuracy becomes more and more. So we can see the distortions which was present. So there was about they almost got reduced by fitting a polynomial to a Sarsky filter. Even after doing this, this is not enough now. Now, so what I you can also use the another filter like moving average filter to reduce this point. But to what I do exactly to get the sharpest point, I use the multiple sensors. I use filter. Then after using Sarsky or the same data which is generated after Sarsky filter, I use the moving average filter. So after using moving average filter, you can see so even at the plus minus 200, the signal was appreciably appreciably converted to a sharp point. And here, even if with this distortion, we get a sharp point. That's it. So actually, these sharp points were important because we needed to pick up this. We have to pick up this point. Now, if it's a lower, the sharp or this distortion was removed and close value to the theoretical signal was considered, and this was used for the further processing. Then, there is other DAQ systems is like battery thermal management system. This is used in electrical vehicles, and this is quite popular. So PLCs and PIDs are also programmed. There are different professional courses available on the PLC programming and PID programming. So PLC programming is it's something like if else control. Now here there is an example I will show. This is a battery and it has a certain temperature. So when this battery is being used, so by using any kind of load or something or continuous use, this battery may so its temperature may rise to a certain value. Like let's say the required temperature is about 30 degrees Celsius and it gets higher to the 35 or 50 degrees Celsius. So what we need is as soon as we need to automate these things so that everything should happen automatically. So this we have used I just showed typical temperature sensor, but temperature sensor will not be actually like this. This is just an example. So this what does this controller will do? This controller will monitor this temperature of this point temperature, this temperature of this battery, and as it becomes greater than the threshold value, what does it will do? It just provide a command to this cooling fan. This fan will turn on and it will blow the air over this, and by using that atmospheric air, the temperature of the battery will be reduced. So this is just a simple example I took so that you can understand those things. Then there is a PID, proportional integral derivative. This is also used in this portion so that the commands you're providing, they should be They should not vary, or there should be minimum error should be there. So by the error which comes under access can be minimized using the PID. You can check on Google, or you can Google them, like you can search the papers and various courses about this. You will get the right, this PID will perform the regulation of temperature. That's then there are different microcontrollers. You can check the manufacturer's website. Basically, for the project purpose, they use an Arduino and the Raspberry Pi. But actually, mm, they are not used by the industries or research institutes. So better microcontrollers are used. This is an XP manufacturer. You can check for different types of. They have different types of microcontroller designed for the different purposes. Now, this is a list of microcontrollers used for battery management system. There are also other like they have designed for electrical vehicles, different types of microcontrollers for the vehicle purposes. So we can go and check this. Yeah. So that's all for now. I think. Yes. Yeah. Thank you.